Alright, let's get started. We begin today's class with this example. You can pause the lecture here to answer this question. Alright, let's take a look. What is the relationship between the expected products of the reaction below? As you can see, it is a reaction of an alkene with a peroxy acid. Peroxy acids have the general formula RCOOOH. So this is an epoxidation reaction. It's going to result in the formation of an epoxide. So let's draw the product. Draw the ring as it is. Draw the epoxide now. These two carbons of the double bond will be part of the epoxide. I've shown you the epoxide on the top, which means the CH3 groups are at the bottom. Right. Now if you take a look at this product, you have two chiral centers in this molecule, two carbons attached to four different groups. However, you have also a plane of symmetry. So this compound is a meso compound. So this reaction will not result in enantiomers. It will result in one single product that is a meso compound. So the answer to this question is only one product is found. Right. Now the next reaction in this chapter is called dihydroxylation of alkenes. Dihydroxylation reaction always results in cis 1,2-diols. Now in the last lecture, we saw how you make a trans 1,2-diol. This is an example of a trans 1,2-diol. If you open up an epoxide with the help of H3O plus acidified water, you will get a trans 1,2-diol. Dihydroxylation reaction always gives cis 1,2-diols. So let's write the reaction. Let's say you start off with that alkene. The reaction conditions for dihydroxylation: osmium tetroxide with some water. That's step 1. Step 2 is sodium bisulfite, NaHSO3. Both these steps are required to complete dihydroxylation. All right. The product in the reaction, cis 1,2-diols. So as you can see, both the OH groups are on the same side. Therefore, it is cis 1,2-diol, because if I call this carbon where the OH is attached as 1, relative to that carbon, the second OH is on carbon number 2. So this is cis 1,2-diol. And if you take a look at this product, you have two chiral centers, but you also have a plane of symmetry. So this is a meso compound. So dihydroxylation reaction will always result in a cis 1,2-diol. The reagents are osmium tetroxide with water followed by NaHSO3. All right. Now one drawback about this reaction is that osmium tetroxide is expensive, extremely toxic, and must be used in stoichiometric amounts. But in the presence of NMO, you can use catalytic amount of osmium tetroxide. So by adding NMO to this reaction, osmium tetroxide is made catalytic. NMO is this molecule. N-methyl morpholine N oxide, abbreviated as NMO. So in the presence of this molecule, you can use catalytic amount of osmium tetroxide. The reason being, NMO regenerates osmium tetroxide at the end of each reaction. All right. So let's now take a look at the mechanism for this reaction. The reactants alkene and osmium tetroxide. Now this reaction happens in one step. It is a concerted reaction, meaning all bonds are broken and formed at the same time. So please follow me carefully how I draw the arrows. The alkene is going to behave as the nucleophile. So you're going to start the arrow from the pi bond, go towards this oxygen. So you're forming a new bond between this carbon and the oxygen. In that process, these pi electrons will go to osmium. Simultaneously, these pi electrons will form a bond with oxygen and this carbon. As a result of that, the intermediate you're going to form is this. The ring as it is. Both the double bonded carbons are now bound to the oxygen. These oxygens are still bound to the osmium. Now if the oxygen bonded to carbon is on the top, the CH3s are at the bottom. So this is the intermediate in this reaction. Now you can have the attack of the osmium tetroxide from the top or from the bottom of the double bond with equal probability. I have shown you the intermediate when the attack happens from the top. You can draw a similar intermediate when the attack happens from the bottom. All right. Now the second step in this reaction, which is NaHSO3 and some water, does not change the stereochemistry of this carbon-oxygen bond. All it does is cleaves this and converts that intermediate to OH. If the oxygen was up, it will remain up and you'll have an OH. The metal groups were down, they will remain down. So the second step does not change the stereochemistry. All right. So as you can see, we have generated a cis 1,2 diol. Both the OHs are cis on the same side, and the relative positions of the carbons bearing the OH is 1 and 2. So it's a cis 1,2 diol. Now if you take a look at this reaction, the stereochemistry of the product is decided in the first step. Because this intermediate that is formed has oxygens attached on the same side, you get a cis 1,2 diol. So the stereochemistry of this reaction is decided in this step. All right. So let's now take some examples of this reaction. Let's say you start off with this alkene. Dihydroxylation conditions. Now because you're starting with an alkene that is cis, the alkyl groups are on the same side, so it is cis. Those alkyl groups will remain cis in the product. So draw them cis in the product. Dihydroxylation gives cis diols. So to the carbons of the double bond, you're going to attach two OH groups on the same side. Now if you take a look at this product, you have two chiral centers in this molecule, but you also have a plane of symmetry. So this is a meso compound. Right. Let's take a look at the bottom example. You're starting with a trans alkene, same reaction conditions. Because in a trans alkene, the alkyl groups are on the opposite side, in the product too, they will be on the opposite side. To the double bonded carbons, you want to add OHs on the same side. Now this molecule is chiral. It's not a meso compound. So you'll form this molecule as well as its enantiomer, because there is equal probability for the osmium tetroxide to come from the top or from the bottom. So you'll form 50% of this molecule as well as 50% of this molecule. These two are enantiomers, which means you'll end up with a racemic mixture. So please make sure you note carefully the relationship between the products. Try to identify a meso versus a chiral compound. All right. So here is a question for you. This question is from the OWL homework. Given these two procedures, A and B, which procedure will work for this transformation? You can pause the lecture here to answer this question. All right, let's take a look at this example. The first step is to identify the transformation that is taking place. You're starting off with this alkene that has a double bond here. And in the product, you have two OH groups attached to the double bonded carbons. And also the two OH groups are cis on the same side. Both have bold bonds. Right. Now the reagent we have learned that can perform this transformation is osmium tetroxide. Osmium tetroxide dihydroxylation will always give cis 1,2 diols. So the reagents that will give this transformation is reagent B. Here is another example for you. You can pause the lecture to answer the question. All right, let's take a look at this example. Again, let's identify the transformation. You're starting off with this alkene that has a double bond here. And in the product, to the double bonded carbons, you have OH attached. But the OH relationship here is trans. One up, one down. The only way we have learned to make trans 1,2 diols is make an epoxide and then open up the epoxide with the help of acidified water. So the reagent that will perform this transformation is reagent A. MCPBA followed by acidified water. All right. So take a note of the stereochemistry in the product to identify the reagent that will allow that transformation. All right. So that finishes dihydroxylation. Let's now move to the next reaction, which is called ozonolysis. This is a very simple, very easy reaction. Ozonolysis of alkenes results in cleavage of the C double bond C. All right. The products are C double bond O compounds. They could be aldehydes or ketones. So let's write the reaction. Let's say you start off with this alkene. Reaction conditions for ozonolysis. As from the word ozonolysis, one of the reactant is ozone, O3. That is the first step. The second step is hydrolysis in the presence of zinc. So those are the two steps you require to perform ozonolysis. Right? And all you're going to do when you're performing ozonolysis is break the pi bond and add oxygens on either side. So you're breaking the pi bond and adding oxygens to the carbons bearing the double bond, right? So you get this as the product. The other product would be this. So as you can see, I've broken up that pi bond and added oxygen. I've given each of the double bonded carbon an oxygen. All right. So this is a ketone, RCOR. This is an aldehyde, RCHO. So depending on the alkene you're beginning with in ozonolysis, you can get aldehydes or ketones. All right. So we are now going to discuss the mechanism of ozonolysis. It's slightly complicated and it's not required for us. All you need to know is how to write the product for ozonolysis. break the double bond, give oxygens to each of the double bonded carbon. Right? It's a very simple, very straightforward reaction. Right? So let's take a few more examples of ozonolysis. Let's say I start off with this alkene. You're performing ozonolysis, O3 followed by zinc and acidified water. Again, break up the double bond, add oxygens. That is one product you will form. The other product, so in this case, you are forming ketones. Both the molecules are ketones. All right. Let's take, for example, this molecule. Again, split it up and add oxygens on either side. Everything else in the molecule will stay as it is. One oxygen here, one oxygen here. Remember, there is a hydrogen here. That hydrogen is there as it is. So if you have a molecule, an alkene, where the double bond is in the ring, you will not split up the molecule. It will become like this. Here, because the double bond is outside the ring, you have broken apart the molecule. Right? Here you have broken apart the molecule, but still it is one molecule. It's not giving you two because the double bond is within the ring. All right. So in this case, you're forming a ketone plus an aldehyde within the same molecule. This is the aldehyde. This is the ketone. All right. So as you can see, it's a very simple, very straightforward reaction. All you need to do is break the double bond, add oxygens on either side. Let's take an example where you do the other way around. Given the products, what is the alkene reactant? You can pause the lecture here for a minute to answer this question. Alright, let's take a look at this question. What is the best alkene that would produce the following two carbonyl compounds upon ozonolysis? So I've given you the products. I'm asking you the alkene that will give these products upon ozonolysis. Right. Now, when you're given the products, the best way to figure out the alkene is drop both the oxygens and connect with a double bond. So I'm going to write this molecule like this. Front of the other molecule and facing the oxygen. All right. So you want to drop the oxygens and connect these two carbons with a double bond to figure out the alkene. So this is the alkene. Upon ozonolysis, will give you those two molecules as the product. All right. So as you can see, it's very straightforward to write the product of ozonolysis or figure out the reactant of ozonolysis. Remember, in ozonolysis, all you're doing is breaking the double bond and adding oxygens to the double bonded carbons. All right. Here is another question for you on ozonolysis. You can pause the lecture here to answer this question. All right, let's take a look at this example. Ozonolysis of molecule A would result in the formation of what functional groups? Anytime you have a question on figuring out the functional groups on ozonolysis, please make sure you write out all the atoms attached to the double bond. If you have hydrogens, please write them out. All right. Upon ozonolysis, you're breaking the double bond, add oxygens on either side. Everything else is going to remain the same. So let's write the product. oxygen and oxygen. So as you can see, you are resulting in two aldehydes. RCHO is an aldehyde. So the answer to this question is option C. Right. So as you can see, it is very straightforward to write the product of the ozonolysis reaction. Right. The last reaction we are going to study of alkenes is oxidation by KMnO4. KMnO4 is potassium permanganate. It's one of the strongest oxidizing agents. In fact, it is so strong, it's used to clean stained glassware in the lab. So if you have a stain on a glassware that's very hard to remove, one of the best ways is to use potassium permanganate. It'll eat up the stain and clean the glassware. All right. So let's take a look at the reaction of alkenes with KMnO4. So let's say I start off with an internal alkene. The double bond is within the chain. The reagents for KMnO4 oxidation is KMnO4 and some acidified water, H3O+. So two things KMnO4 does. First, like ozonolysis, you'll break the double bond, add oxygens to the double bonded carbons. The second thing KMnO4 does is, if you have a hydrogen attached to the double bonded carbon, it oxidizes that hydrogen to OH. So both of these hydrogens, because they're attached to the double bonded carbons, will get converted to OH. So let's write the product. So you will generate two molecules of carboxylic acids. Now since the R groups are same, you're going to generate two same molecules of carboxylic acids. If the R groups are different, you will generate two different molecules of carboxylic acids. All right. So let's now look at a terminal alkene upon oxidation. A terminal alkene has the double bond at the end of the chain. So you have a CH2 at the end. Same reagents for oxidation, KMnO4, H3O+. Upon KMnO4 oxidation, you split the double bond, add oxygens on either side. Any hydrogens attached to the double bonded carbon will get converted to OH. So all these three hydrogens will get converted to OH. Let's write the products. So that is one of your product, carboxylic acid. The other product, this molecule is H2CO3, carbonic acid. And carbonic acid will split up into carbon dioxide and water. So only terminal alkenes form carbon dioxide upon oxidation by KMnO4. And that carbon of the carbon dioxide is coming from one of the double bonded carbons. So that terminal carbon of the double bond gets converted to this molecule, which further produces carbon dioxide. All right. So that is about oxidation by KMnO4. Let's look at some examples. Let's say I start off with this molecule. I perform KMnO4 oxidation. Split up the double bond, add oxygens on either side. Any hydrogen attached to the double bonded carbon gets converted to OH. Let's write the products. Rest of the molecule is going to remain the same. So you're going to form a molecule of a ketone and carboxylic acid. Let's take another example. This time a cyclic compound. Let's say I have this molecule and I perform KMnO4 oxidation. The double bond is going to split up. You add oxygens on either side. There are no hydrogens attached to the double bonded carbon. All right? Rest of the molecule is going to remain as it is. So you're going to form this compound that has two ketone groups within that molecule. All right. So as you can see, it is very straightforward to write the products of KMnO4 oxidation. Split up the double bond, add oxygens on either side. Any hydrogens attached to the double bonded carbon gets converted to OH. Rest of the molecule remains the same. Only terminal alkenes will form a carbon dioxide. And keep in mind that carbon of the carbon dioxide is the CH2 carbon, the terminal carbon of the double bond. All right. So here is a question for you on KMnO4 oxidation. This molecule has two double bonds. Please note there is sufficient KMnO4 to react with both the double bonds. You can pause the lecture here to answer this question. Alright, let's take a look at this example. You're reacting this molecule with KMnO4. And as I mentioned, you have sufficient KMnO4 to react with both the double bonds. So let's write the product. Split up this double bond, add oxygen on either side. Similarly, split up this double bond, add oxygen on either side. All the hydrogens connected to the double bonded carbons get converted to OH. Everything else remains the same. So let's write the product. That becomes a ketone, this carbon. This carbon becomes a carbon dioxide. It's a terminal carbon, it's a CH2, so it will form carbonic acid. Carbonic acid splits up into carbon dioxide and water. So that is this part of the molecule we have written. Let's write the other part. So you're going to end up with two carboxylic acids and a ketone in this molecule. And this terminal carbon is going to get converted to carbon dioxide. So the answer to this question is option D. That finishes all the reactions of alkenes and chapter 8. Now I know in this chapter we have gone over a lot of reactions, so I've summarized all the reactions in a slide. Now a couple of things I want you all to note while you use this slide to study. 1. I have shown you only one of the enantiomer written as the product. Please understand, if the reaction is forming a chiral center, you will also get the other enantiomer in equal quantity. I have not written it just for the sake of saving space. Alright. The second thing you want to keep in mind is don't memorize these reactions. Right? Try to understand how you form the product. For example, we have studied 3 reactions where we have opened up a 3-membered ring. Anytime you open up a 3-membered ring, the reaction will generate anti-stereochemistry. For example, if you open up an epoxide, you will get anti-stereochemistry. In the case of halogenation, you will open up a 3-membered ring, you get the halogens with anti-stereochemistry. In the case of halohydrin, again you open up a 3-membered ring, you get anti-stereochemistry. So anytime you go through a 3-membered intermediate and you open that up, you are going to get anti-stereochemistry. So if you understand how the reaction is taking place, you'll be able to figure out to write the product. Alright? So please don't memorize these reactions. Try to understand them and solve examples from class notes as well as OWL. Alright? The next chapter we begin in the semester is chapter 11, nucleophilic substitutions and eliminations. Now, so far in the semester, we have majorly focused on electrophilic addition reactions. Whether it's an alkene or an alkyne you begin with, the first species that attacks the pi bond is an electrophile, and the overall reaction is an addition reaction. You add species across the pi bond. In this chapter, we are going to look at substitution and elimination reactions. The key idea of this chapter is in a substitution reaction, you are substituting one group with another group. In an elimination reaction, you are removing atoms from adjacent carbons and forming a new pi bond. Now, as you can see from this picture here, both substitution and elimination require alkyl halides. The starting material is an alkyl halide. Right. Now, the substitution reaction I've written here is a nucleophilic substitution reaction. The reason being, the species attacking the alkyl halide is a nucleophile. OH- is a nucleophile, it's electron rich. So the first species approaching the alkyl halide is a nucleophile. Therefore, this type of substitution is called a nucleophilic substitution. Now, based on the reaction mechanism, nucleophilic substitutions are classified into 2 types, SN2 and SN1. So let's begin this chapter by looking at SN2 reactions. SN2 stands for substitution, nucleophilic, bimolecular. So this 2 stands for bimolecular. All right. So let's understand SN2 reaction with a simple example. Let's say I start off with this alkyl halide, CH3Br. I react with a nucleophile OH-. So this is the nucleophile in the reaction. As we have learned in previous chapters, the carbon-halogen bond is polarized towards the halogen. So the carbon in the alkyl halide is the electrophile. Draw the arrow from the nucleophile to the electrophile. In that process, Br will leave. So as a result, you form a new bond between oxygen and the carbon. This is the new bond you have formed. Br has left with the electron, so it is the leaving group. You form Br-. So this is the leaving group. Any species that leaves with a pair of electrons is called the leaving group. So Br- is the leaving group in this reaction. This is the new bond you have made. Right. So let's look at this mechanism in more detail. So here is the reaction again. OH minus is the nucleophile reacting with the alkyl halide. This is the new bond you have made. And Br minus is the leaving group. Now the experimentally found out rate law for this reaction is rate equals rate constant times concentration of alkyl halide times concentration of the nucleophile. Now if you remember your general chemistry 112, the exponents in a rate law are called orders. So the order with respect to Rx is 1. I have not written anything there. It's understood to be 1. The order with respect to nucleophile is also 1. And the overall order of the reaction is sum of all the exponents. So the overall order for this reaction is 1 plus 1, that is equal to 2. So it is a bimolecular reaction. And that is what this 2 means in the SN2. The overall order is bimolecular, and that is why you have that 2. All right. This also means anytime you want to speed up the rate of an SN2 reaction, the best way to speed it up is increase the concentration of both the alkyl halide and the nucleophile, because both are part of the rate law. Right? So that is the best way to speed up the reaction. Now the SN2 reaction is a concerted reaction, meaning all the bonds are broken and formed at the same time. It's a one-step reaction. So let's now draw the reaction coordinate diagram for an SN2 reaction. The y-axis is the energy. The x-axis is the progress of the reaction. You're starting with your reactants, the alkyl halide and the nucleophile. These are your products, the alcohol and the leaving group Br minus. Concerted reaction means it's a one-step reaction, therefore you have one hill. The topmost point in the hill is the transition state. Now one key point about the SN2 mechanism is that the incoming nucleophile must approach the electrophile from the opposite side of the leaving group, and this is called the backside attack. So let me show you what this means. You're starting off with this alkyl halide. This is the nucleophile OH minus. The OH minus should approach this electrophilic carbon in the opposite side of the leaving group. The leaving group is this side. The OH minus is coming from the opposite side. And this is called the backside attack. And the reason this is required is because the best overlap of orbitals required to form the new bond between the nucleophile and the carbon is only possible if the nucleophile approaches from the backside. So always keep in mind, in an SN2 reaction, the nucleophile should approach from the opposite side or the backside of the leaving group. All right. So let's now draw the transition state for this reaction. Now if you remember chapter 6, we said transition state is a snapshot of the reaction as reactants are getting converted to products. So in this reaction, as reactants are getting converted to products, the carbon-bromine bond is breaking. Bromine is leaving as Br minus. At the same time, carbon-oxygen bond is being formed. The rest of the bonds are remaining as it is. They are not getting affected. Right. Now Br is leaving as Br minus. It's in the process of leaving. It has not left completely. So as of now, it has a partial negative charge. OH minus has come in with a negative charge. It is given that negative charge to form the new bond. So you're forming the new bond, so as of now it has a partial negative charge. So this is the transition state in this reaction. Now as you can see, it is not straightforward to represent transition states on paper, but the reason I'm showing you this is to tell you that this reaction is a concerted reaction. Bonds are forming and breaking at the same time. It's a one-step concerted reaction. All right. Now let's go back to this backside attack. Due to this requirement of backside attack in an SN2 reaction, it results in inversion of stereochemistry. So let me show you with the help of an example what I mean by inversion of stereochemistry. Let's say I start off with this molecule. Let's say I start off with this molecule. As you can see, this molecule has a chiral carbon. This is the chiral carbon. For the reaction to happen SN2, you should have the nucleophile approaching from the opposite side, from the back side. So let's say the nucleophile comes from here. In that process, bromine is going to leave. Right? So let's write the product. Rest all the bonds are going to remain the same. The leaving group is Br minus. Let's now first figure out the configuration of this carbon. In the reactant, the chiral carbon, is it R or S? Br gets priority 1. Hydrogen gets priority 4. CH2, CH3 gets priority 2. CH3 gets priority 3. Start the arrow from 1, go towards 2. This looks clockwise, but the fourth priority group is coming towards you. So actually the configuration is S. Let's now look at the configuration of the chiral carbon in the product. Again, this is the chiral carbon in the product. Oxygen gets 1, hydrogen 4, CH2, CH3 2, CH3 3. Start from 1, go towards 2. That's a counterclockwise, but the fourth priority group is in the front, so configuration of this molecule is R. So as you can see, you started off with S, you have got R. And this is what I mean by inversion of stereochemistry. So if you start off with a chiral center, an alkyl halide that has a chiral carbon, and if that alkyl halide undergoes an SN2 reaction at that chiral center, the product will have the opposite configuration with what you began with. If you start with S, you will get R. If you start with R, you will get S. So always an SN2 reaction will be accompanied by inversion in stereochemistry. All right. So key points about SN2 reaction: it's a bimolecular reaction. Overall order in the rate law is 2. The rate of the reaction depends on both the alkyl halide as well as the nucleophile. Second, it's a concerted reaction. It's a one-hill, one-step reaction. Bonds are breaking and forming at the same time. Third, always the incoming nucleophile should have a backside attack on the electrophilic carbon, opposite to the leaving group. Finally, due to this backside attack, you will always end up with inversion on stereochemistry of the product. All right. So here is a question for you on SN2 reaction. You can pause the lecture here while you answer this question. Alright, let's take a look at this example. Draw the structure of the compound you would expect from SN2 reaction of the molecule below with NaCN. NaCN splits up into Na plus and Cn minus. So Cn minus is the nucleophile in the reaction. Na plus is a spectator ion. Don't worry about it. So the nucleophile in the reaction is Cn minus. This carbon is electrophilic, iodine partial negative charge. So Cn minus is going to come from the back side, iodine is going to leave. Now because in the question I've told you it's an SN2 reaction, if you're starting with a chiral molecule and the reaction is taking place at the chiral carbon, you should get inversion of stereochemistry. So let's first figure out the configuration of the starting molecule. I'm drawing the starting molecule here again. Iodine gets priority 1. This carbon gets priority 2. CH3 gets priority 3. Hydrogen is in the front. It gets priority 4. So start from 1, go towards 2. That's a clockwise. But since your fourth priority is in the front, the actual configuration here is S. So the product should have the Cn minus on the carbon and the configuration should be R. You have to get an inversion of stereochemistry. Now if you take a look at option C, Cn gets priority 1, this gets priority 2, CH3 gets priority 3, hydrogen is in the back, priority 4. Start from 1, go towards 2, the fourth priority is in the back, this configuration is R. So the answer to this question is option C. All right. So always keep in mind for an SN2 reaction, if you are starting with a chiral carbon and the reaction is taking place at the chiral center, you will get an inversion in stereochemistry. In this example, you started with S. The product should be R. All right. So we'll end today's lecture here. Please let me know if you have any questions regarding today's lecture. Have a good rest of the day.